Welcome. Hello, everybody. I'm Atlas. I like to do stuff. So anybody else out here that likes to do stuff? Hi. Yeah, 2 or 3 of you, right? And I love the fact that in the last couple of years, it's become apparent that the hacker crowd is not just bent on throwing Metasploit or hacking, throwing some SQL injection or whatever. It's about doing stuff. It's about doing stuff and kicking ass, right? So today we're going to talk about a toy that I put together a couple of years ago called RFcat. Now, the title that I'm putting on the training that I'm trying to put together for Black Hat is RFcat is your friend. Oh, come on. Can't be that old. All right. The intro to this is a little awkward. So here's the deal. I have modified, improved, made Mo better for a couple different talks. I've given this base talk at about 3 major cons, and I've never been able to finish it. Why? Not because I suck. That's a totally different issue. We'll talk about it later. I do suck. But it's just too much information. So 2.5 hours shrunk down to 50 minutes never works. I actually saw blood dripping out of a few of the people's heads. So what I ended up doing was I said I hit the big 3. I've had a good run. So GerCon, which I talked at 2 days ago, and DerbyCon, we're going to see the rest of the party. Okay? So what I've done is I found that there's actually a dividing point in the talk where everything before it was lead up, very valuable lead up, I think. But I think from there, it's a complete self-contained talk in and of itself. So that's what we're going to do. It went pretty well with GerCon, so I'm going to do the same today. I think that you'll like it. But if you say, man, what the fuck? DEF CON has the video. Go check out the first half. All right? Thank you. So from the original half, there are 2 slides I'll hit on, 2 or 3 slides. First of all, if you want to go find the code or slides, rfcat.google.com. Googlecode.com, sorry. There are several different releases of the presentation. The Black Hat slides are the best because they include exercises. Understood? I've modified very few things from the end of the talk. Why? Because I know you're going to be looking for me to give that talk, but you've never seen it. So I'm going to give it today. How many of you have used wireless in the past? How many of you are using it right now? Yeah, exactly. So 2.4 has been the poster child for wireless networking. And it's a great thing. It's got some standards. You probably have cards that have adhered to these standards and charged lots of money for them. We're about to talk about the Wild West of networking, wireless networking. In that, you cannot just go buy a dongle or get it in your laptop stock, something that says, subgigahertz, you're mine. And a few years back, this became very important to me, that we be able to have this capability, particularly as reputable, kind-hearted, gentler security professionals. There are some laws about what goes on in what is called the ISM bands, which is what we're going to focus on largely because I built a tool that uses a radio that does the ISM bands really well. It can do a little bit more than that, but that's a different discussion. Popular ISM bands, 300 megahertz, 433, even though that looks like a very strange one, 868, 915. Now there are other frequencies are like around these, but these are the general focus points. There are other dongles, however, that I've been working to include into the RFcat family, which will allow 2.4 gigahertz and maybe some Zigbee. Anybody want some Zigbee action? Yeah. Now, frequently asked questions often include, why can't you just do this in in GNU Radio? GNU Radio is really amazing. What's that? I would not say that. So yes, GNU Radio is an amazing project. If anybody is not familiar, a software-defined radio with some open source software, and you basically have raw waveforms coming into your computer system for you to pack up, slice, dice, generate. Really, really cool stuff. It's a lot of freaking work every time. So the idea was, in the work that I was doing, which may or may not have had something to do with a power grid, the devices that I was hacking used this radio, the ChipCon 1101 radio. And there happened to be one that also had a USB controller on it called the ChipCon 1111 and a microcontroller. Boom. So this project got started. There may be some more extensions in the future. We'll see. What plays in sub-gigahertz space? Sexy ladies wearing insulin pumps. That's what my grandma looked like. Cordless phones, your remote keyless entry. Keyless entry? Yeah, that's what RKE means. Little girl toys. Who here loves the little girl? Let me rephrase that. All right. How many of you like the pink I am me? Yes. For the technical things you can do with it, not for any like creepy, lecherous things. Power meters. Your own devices. I know of at least one person in here who is resonating with that concept right now. We're going to be taking down your copters, buddy. TI's actually put out a Kronos watch. It's a kludgy looking thing. It's really thick and doesn't flow well. You would not get this from Gucci. However, the concept was, let's make a radio-enabled watch and see what the freak people do with it. So they've released this concept, and in fact, AtlasRfcat first started working on the AtlasRfcat, or I'm sorry, on the Kronos dongle, the thing used to program it wirelessly. We repurposed it. Very cool toy. And your cell phones. I think I'll stop there. How do we play with it? Well, this is my talk, and I wrote a tool called AtlasRfcat. So guess what my answer is? Yeah, AtlasRfcat. Oh, come on. That's the best you can do? I expected Sean to be all... Oh, you're drinking something. That's what. Got it. So here's where we take a time warp into the second half. Intro to AtlasRfcat. We're going to talk a little bit about background, a little bit about our goals, some of the plans, and where we're at so far. And where we're at so far is actually the part that that has continued to progress. We've had a lot of very smart people contributing. Well, okay, a couple very smart people contributing a lot of features, bugs, and otherwise. Yes, they introduced bugs too, but it was a lot of fun. Back in about 2008. I was approached by some power people, and they said, we are rolling down the road at about 100 miles an hour towards this thing called smart grid. There are some people in the industry who know this may or may not be a good idea. Let's figure it out. I know that you can do stuff. Let's go do stuff. The goals, as I found out about 3 years later, were A, to break the shit out of their systems, prove that there are problems, and B, scare the shit out of the vendors so that they're proactive. In fact, the B was actually, I think, more foundational to the salary that, or the income that I was making. So, and actually, I think that it effectively worked largely. I was at Distributech in 2008. I love walking around, so see if I can still see you guys. Hi. So I was at Distributech, and this is a big utility thing. Oh, I'm going to make your life hell. In Distributech, I got to meet some of the vendors that I was going to be playing with. And some of them that actually didn't make the cut. And I won't tell you which camp this particular vendor was in, but I had a conversation that went a little bit like this. Don't worry about it. Our frequency hopping spread spectrum is so fast, hackers can't hack it. Two problems with this thought. First of all, what? What you're saying is that you're going to throw down a gauntlet like that and hackers could never hack it. I didn't hear any proof there. Second problem, actually fairly endemic of the whole arena of power, they didn't understand what hacking meant. The people I was speaking with glommed onto something, information disclosure, taking over, blah, 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 and basically thought if they can't do a PCAP dump of it, they can't control it. This was actually a serious problem. Anyway, long story short, let's move on to the tool. I don't want to rip on too many people too fast early in the talk. So the RFCat goals, well, I love radio. I've loved radio since I was 5. The idea of the little crystal thing that, wow, that still excites me. The idea of waves, electromagnetic waves going through the air, causing cancer worldwide is really exciting. It also had a lot to do with, obviously, my security analysis work. And overall, I just like to break things. I like to understand how they work. I like to understand better than the people who designed them how they work. Back in 1903, there was a face-off between a guy named Giuliano something Marconi and Neville Maskelyne. Now Marconi, if anybody is in radio here, who's heard of Marconi? Marconi, not the man, but his company, which still persists today and is a huge name among radio, right? So Marconi had this idea that his company had developed the latest, greatest radios that they could tune very precisely to a particular frequency. And by tuning directly into this little frequency band, they basically created the first conceptual virtual private network. Marconi was saying, I can split up the spectrum and send your data over this little bit, and it's like private, right? And Neville went on to prove some nastiness, and we'll get into this later. Okay, yeah, I guess I did write it down. Guglielmo. Hi! So anyway, oh, really? Yeah. Hey, she gets it. You guys don't. For those of you who had seen the talk that several of my friends and I gave about Heady Attack to determine hopping patterns of wireless networking, this is not Heady Attack. It was based on a lot of the work that we did to learn how to do Heady Attack, and in fact, I think it improved upon some of the USB concepts that we use for Heady Attack. The idea was, yeah, great, so we find out a hopping pattern for a given networking system. Then what? RFCat was the then what? Can I develop a toy that, at least in my personal repository, I put in a hopping sequence and it syncs with a power network? Well, we'll see. RFCat has several different faces, as you will. The first one is my favorite. It's easy, comes up as basically either a direct link between you and the RF spectrum, or in research mode, the command line tool drops you into an interactive Python shell. Creates an object that talks over libUSB to the RFCat dongle. So when I type in commands in research mode, I type d dot, because D is the name of my dongle. Yes, I know, I did not go through the ceremony of a dongle naming for that. However, it allows me basically Pythonic access to the sub-gigahertz radio range. Second interface is RFCat server. This stemmed from a couple other products that I had seen where rather than having a driver that has some basic interface that software plugs into, in Windows, plug in the dongle, and this server would listen on a TCP port And then the clients would connect to the TCP port and not have to mess around with drivers and all that directly. So RFCAT server follows this concept. You start RFCAT server, you connect on a TCP port 1900, and that is your back and forth with the wireless spectrum. And you connect on port 1899, just a step below, and you can configure all the parameters in an interactive CMD way. Those of you not familiar with that, check it out. It's fun. To get into research mode, we type rfcat-r, and I think that's where the power mostly is. Here's some examples of interacting with the dongle. For example, d.rfxmit. That sends blah, or whatever you want. You receive using d.rfreceive, and a couple other various tools we will talk more about in a little bit. Some of the best parts about interactive Python is that in my code I can write documentation, and by typing help d, you can see the documentation. I don't have to write some PDF book or whatever. This is a screenshot, however poorly done, of RFCAT server. You see in the center, or you see over here, we run RFCAT server. We connect on, actually, sorry. We run RFCAT server over here. We connect on port 1900. I can see that, can't you? Sorry. And here is 1899, and with some, with all the commands that are available, you just type help. Pythonic. My voice is my Pythonic. Verify. Now, my personal favorite interface, although not quite as powerful as the Pythonic interface, is the IME-sniff interface. So I didn't really know how it made sense to break down the firmwares originally, so I had it all spread out. RF-sniff, RF-NIC, RF app, FHSS NIC. So like breaking it all down. Major Malfunction and I are kind of in the process of merging them back together. But AppSniff was really special because AppSniff very easily converted using some code written by Mike Osman and another gentleman, I forget his name, and allowed me to make a sniffer out of an IME toy. The beauty here is this is a very static thing. It doesn't depend on USB. It doesn't depend on the settings that I have in one given environment. This is pretty static. I'm able to configure the radio settings using the keyboard with like a breakdown. There's a README on what the key settings are. I'll show them on the next screen. But when developing a transmit and receive system where I'm writing the whole thing, you get into this quandary of, it's kind of a chicken and an egg quandary of, okay, that didn't show up on the other end. Which side failed? So the sniffer allows me the ability to capture all sorts of information about the wireless going on around me, but more particularly in my case, it allows me to see, yeah, it's transmitting. This broke on the receiver side. This is a README file that's in the project, but I threw it up here. It lays out what the keys are for, how to increment, bandwidth, modulation type, sync word, blah blah blah. Speaker button. This is kind of fun. Speaker button allows you to just put it in transmit mode. What's transmit carrier mode? Well, it's a very small jamming mechanism. Wrapped in not too long ago, just a couple months ago, I put a spectrum analyzer on here. Many thanks to the Ubertooth folks, in particular Mike Osman, whose GUI I literally just stole and then inserted my own data inputs. So from the Python command line, type d.specan, and all three parameters are optional, and it'll default to 902 range and some sane settings to get a bit of the 902 range. But here I use the Pythonic scientific notation. 901E6. What's that? Anybody? 901 megahertz, exactly. E6 means add 6 zeros. So 5E5, what's that? $50,000 hertz, 50 kilohertz. That's the channel spacing, so how wide between my samples. The spectrum analyzer just runs through the spectrum and samples the power, right? Okay? And then I'm using 51 channels. So this defines what the data, how the data is laid out on the screen, as well as how the radio traverses through. There are some limitations, namely the lowest channel spacing is about 23.4 kilohertz. Can't get lower than that. The highest channel spacing is 250 kilohertz. And it's limited to only sampling up to 255 frequencies in one pass. That's actually a lot more than you need. I recommend about 100. Otherwise, it kind of takes a little slower. You may actually miss data. Has some limitations. It's not the $50,000 or the $200,000 spec an, but it's not bad for $50 or $100. So to break it down, some of the coolest parts of AtlasRfcat are listed on this screen. I'll go through them just a little bit. There's a variable on the D object called _debug. It's defaulting to 0. No, as in turned off. You set it to 1, and you get to see a sane amount of information going back and forth between the Python client and the firmware. These bytes were sent. These bytes were received. If you set that to 2, it gets a little more insane. 3, quite a bit more insane. And 4, you just write out. But it can be very helpful, and just scroll back and find your bugs. The debug function, however, scrolls through periodically, much like a top fashion, only without the libread line. And it just spits out some interesting information, the state of the dongle over time, including how full your buffer is in the Python side. So when you receive data from AtlasRfcat, it immediately sends it over the USB. And the Python, which has way more memory available to it, I'm hoping, unless you use like a netbook from like Origin. Yes, I just said that word. Discover. So the idea, there are a few complexities about sub-gigahertz radio in that everybody just basically rolls their own. They do their own thing. Oh yeah, well mine's compliant with C12. Yeah, right. That's way high on the networking model. The sub-gigahertz MAC and PHY is all defined pretty much per device. So when you've got an insulin pump, they set up all their radio parameters, and they set up the protocol that things go back and forth on, down to, and actually quite more importantly, including what's called a sync word, or a start of frame delimiter. What goes on in a radio, when you start to see, when your radio, okay, think like a radio now, get out of hacker mode for just a minute, and be the radio. There's noise all day long. The sun makes noise. Your cars make noise. There's electromagnetic interference all the time. So what the radios do is, in the hardware, at a very fast pace, they have a packetting mechanism that waits for a carrier of ones and zeros. 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. After a certain number of ones and zeros that it can clearly identify as, they're not dicking around. This is actually something that we want to pay attention to. They then start looking for a start of frame delimiter. Most systems, not every one, okay? Important fact, everybody rolls their own. Keep that in mind. But most of the more advanced systems look for a start of frame delimiter. It is typically 2 to 3 bytes long. And after a certain amount of preamble bytes, that's the 1 0 1 0 1 0, and if it starts to see the start of frame delimiter, at the very end of the start of frame delimiter, it knows the packet starts here. Discover mode was created specifically to weed through raw data dumps that don't wait for a starter frame delimiter, because that would actually limit us to one particular type of device. It waits for bits to come down, displays them for you, and if it can find bit patterns that look like a preamble followed by a sync word, it gives you a list of possibilities. These are the things that the sync word might be based on what we're after. It'll also take the ability to, it'll also allow you to search for particular sync words. For example, hacking a power meter, I happen to know that there are 15 possibilities for this power meter for sync words. They do this because their meters are used in wide geographic locations by different systems, and they don't want the overlap. They want, in a hardware way, the radios from this utility to ignore the radios from this utility. Pretty cool. I mean, that's actually pretty decent use of engineering. So they have 15 different starter frame delimiters. So I put in a list. These are the starter frame delimiters. You can get those in any number of ways, including pulling and reversing firmware, or hey, just getting access to the source code, or something like that. Discover mode lets you do all that. Discover mode heavily relies on something that I created, and you have to put up with my naming. Why? Because I wrote the tool. If you want to name stuff yourself, write your own damn tool. Lowball. The concept of lowball is simply to remove all reasons why your radio might not pass you information. Pretty cool, right? So you have a default configuration. Lowball saves that off, actually, so that it can be restored later. And it says, okay, nope, turn off forward error correction, turn off MD5 or CRC checking, turn off starter frame delimiter, turn down the preamble quality threshold to 0. So, it just, as soon as it feels that there's power, start sending bits. Lowball restore, what do you think that does? Aside from reading the screen, that restores the configuration that was saved when you entered lowball. So that it's not this painful thing, oh, I ran this cool thing and now I have so much work to set my radio back to the original config, and I hope I got it right. I didn't want the troubleshooting problems, so I added this. RF listen, which is a simple, nice command line way of saying, if you have packets, please show them in a nice hexadecimal fashion on the screen, and I'm just going to sit here and listen. RF capture, on the other hand, does the exact same thing, but when you hit enter to leave listen mode, it returns a list of all the packets that it had captured along the way. So that if you want to actually see what's going on and then have a chance of doing analysis later if something interesting pops up, you can use RF capture mode. Something I literally wrote. No, I didn't write it while I was driving down the road. That would be stupid. But for driving down the road, driving through town, a tool called scan simply takes in some parameters of how big of a frequency jump to do, how frequently, and sits and listens on a set of channels, starts spitting stuff out. I discovered at my house, which is like a virtual RF cage because I can't see my closest neighbor, that at 912 and 924 megahertz, there's a lot of activity, like pretty constantly. Still haven't figured out what that is yet. But if anybody knows, you can tell me offline. Thank you. I thought you were at 5.8. Damn. Yes, you guys would. SpecAn. This pops up the GUI, gives you the cool little graph. I just like pretty looking things. So, and then d.print radio config. This will pretty much print an entire screen full, telling you the frequency, the modulation type, the bandwidth used per channel, what channel you're on, all this radio type information. And then information about the client, how many packets we've received, are we in a good state, are we actually able to talk to the dongle, this type of thing, and makes it pretty on your screen. And we talked a little bit about lowball and lowball restore. Lowball takes different varying settings, however. So lowball 1 is the default. And this says as soon as you see power that reaches a certain level, and as soon as you see that we're receiving, send me the data. Lowball 0 is just send me the damn data. I don't care if there's power. Send me the sunspots. Just give it to me. Discover uses lowball mode. We already talked about that. Discover handing in a lowball entry will use that lowball level for Discover. Ident sync word turns on the subsystem that looks through the bits for a preamble and then gives you the possible sync words that it could be. And the parameter sync word match list equals, and you give it a list, turns on ident sync word and then spins around searching for a list of sync words and makes a big deal about it so that you know when it happens. I had to use the title. Please forgive me. You need a couple more tools to really do an awesome bang-up hardware thing. But for attacking only, once you know what's going on, RFCat is the one to rule them all. My typical setup is to use my dongle Gina. Yes, I do participate in dongle namings. Running RFCat with a spectrum analyzer. Paul, may he rest in peace. Paul was stolen from me at ShmooCon. I hope he's found a good home. But another one using Kevin. Yeah. They're old slides. And I am me running RF sniff. Why? Because I like to know that I'm seeing multiple things, multiple perspectives into the same thing. Possibly an IME running spectrum analysis. This is what it used to be before I wrote the spec-an code. Mike Osman's spectrum analyzer, really awesome thing. Actually taught me a lot about spectrum analyzers. During the discovery phase of what in the heck this thing is and how it works, outside of the RFCats and the IMEs, I use a Celea logic analyzer to tap bus, watch bits flying back and forth and make sense of them. I think that it is by far the best low-cost whatever kind of analyzer that is, a logic analyzer, that you can buy, and you should. I also use a FunCube dongle, although, unless you're trying to transmit, turns out there's a $20 dongle that you can buy, made for video, that allows you to, strangely enough, it allows you to do a lot of the things that a normal SDR allows. And the only thing that I use an SDR for is looking at the raw waveform to determine some of the parameters, just because it's actually easier. I keep trying to make RFCat compete in this arena, trying to make it easier, doing binary analysis, looking for, setting the bandwidth to as high as it goes, and then analyzing the bits, trying to figure out what the waveform looks like. But in reality, at the end of the day, currently, an SDR just does it easier. So that's why I use the tool. I created an RF attack form a while back, and you can download it here at my blog site. Basically just kind of runs through and says, hey dude, are you really thinking of everything? When you're doing your analysis, anybody else find it hard to shift gears sometimes? When I'm working really hard on something, hardcore, and then I go into, let's go learn about something, sometimes I may not always remember everything that I was thinking the last time I did analysis, so this gives me a good guideline to go by. And other people have found it interesting, and so I created a PDF for it. So the part that all those other people who listened to the talk earlier in the year missed out on was the good stuff. The stuff about, okay, what's so cool about this? Now, a little disclaimer. Some of the work that I did here was done way before RFCat was where it's at today. So some of the stuff that we did was just kind of slamming around, trying to find information so that we could make RFCat do its thing. Because back then, I really thought of it mainly as a tool for attack, sending, and sniffing, once you already knew about something. The more important disclaimer, mucking with medical devices is dangerous. Be responsible, be careful. If you were to do this, make sure that you know every bit that you throw around the air, and that you know that it is directed at the device that you think it is. One of my best friends uses the pump that I'm about to tell you about, and this is very near and dear to my heart. The initial thing that I found, was that in the PDF manual that I downloaded from the device's website, told me exactly what frequency to go to. Yay! As if every diabetic were a hardware hacker or RF hacker. Why do you need to know what frequency you're on? I don't know, maybe because, you don't want my secondary insulin pump. I don't know. Why? I liked it, but I don't like it at the same time. So I did some analysis at that frequency, and just honestly, having dorked around with the RFCat enough with a spectrum analyzer to know what it looks like when I transmit different modulation schemes, I was able to pretty much snap it out of the air, confirmed it with Mike Osman, and we both agreed this is modulation, and it was. So what's the lesson there? I didn't teach you anything, right? I taught you, go to the RFCat, get an turn on spectrum analysis, flip through your modulations, and learn for yourself, right? I'm not going to make this easy just because I need you to actually want it and to be responsible with it. We also, so here, it's kind of funny. I'm preparing for my first talk on this, and I'm jabbering back and forth with Mike Osman. I'm like, this is really frustrating me. I'm getting stuck on this problem and this and that. And he says, shoot me a USRP dump. I'm like, I don't have a USRP. He says, you got this far without a USRP? Really cool. I think I'll send you mine. And at this point, he had not really contributed to the project at all, except to be a friend and, walk me through some of the difficulties I created for myself. So he literally drop shipped overnight his USRP1 and then walked me through compiling GNU Radio. It works like, just point of interest, the Ubuntu repositories for GNU Radio, they're decent for some stuff, but yeah, they kind of suck. Uninstall them, compile from source. Mike Osman, hit me later. I've got an email from Mike Osman that he sends out to his class before they show up so that they've got it compiled. So it worked right away. So I like the look of PCBs. That's why they show up on the presentation, and that's why I tear things apart. So the first thing that I did was I cracked in, took my logic analyzer, plugged it into what looked like a bus between a daughter board, which I swore at the time was a radio, and it turns out I was right, and the main board, which does all the logic and reads in, I don't know what it does to analyze the blood, and then controls the screen. So tapped that and got nowhere. So major fail in a good way. The good way is that that the guys that you're coming to listen to, hopefully that means you got some respect for me, unless you got some like arsenal that you're going to throw at me at the end. I fail. Okay, I take a stab in a direction, doesn't get me anywhere. It's not a loss. The data that I get there, not only does it keep me current on whatever that technique was, but the data that I get there often plays into analysis later. Moved on, used the USRP, captured the data going back and forth from the meter unit down to the pump. And I was able to get an idea of what I should be looking for. I was able to grab baud rate just from the wave pattern. You break it down by milliseconds and you can kind of figure out how fast it's going. I was able to figure out the start of frame delimiter and confirm what the modulation was. Through the dump out of the USRP into a tool called Baudline. This is something that Mike Osman recommended. Also, he threw it through GNU Radio Companion, which honestly I hoped never to be an expert on, because it is a large bit of mumbo jumbo that looks like the inside of a radio and less like whatever. Anyway, so we were able to dump the information, do analysis, confirm what we had thought from a couple different routes. And, well, here's the GNU Radio Companion screen and why I don't ever want to be an expert. Down here you see the waveform. Here is the preamble bits. Here's the start of frame delimiter, and the data follows. And this is what baudline looks like. I'm not going to explain it, but when you're in baudline, I want you to feel comfortable. Hey, you know, I've seen this before. This is what's showing up here. We're somewhere close. Let's do some analysis. Once we identified what we thought to be the parameters, we plugged in the configuration into AtlasRfcat. And lo and behold, AA, what's that in binary? Anybody? Yeah, it sounds a lot like a preamble, doesn't it? 10101010, that's AA, and then some. And then we saw what we had identified as the start of frame delimiter. And so I turned it out of discover mode and just put it into RF listen, and it spit out exactly what I anticipated. This was what we were looking for. This is where the research has stopped right now. There are a couple avenues that I'd like to go down as time permits. I know that there's a device that is actually able to push insulin, not just make things show up for approval on the pump, and I want to get into that. Not because I want to kill anybody, although I'm sure some people do, but because I want to make it very painfully obvious to those who are responsible for these things that they're broke. I am, however, able to register glucose levels of 475 and above, and that's pretty killer. Now, I apologize. I actually did not bring the power meter, and it's a good thing because I don't even have a table here for my audio visuals. Normally, I like to drag around a power meter and get charged extra from Delta. Caution, playing with a power meter without authorization is illegal. And not only illegal, it can cause a lot of damage to you and to others in some states. Nice. Okay, your power company may not like you very much, and it's illegal to steal somebody else's power meter. How's that? No, doesn't work. You point me a link to a smart meter on eBay, and I'll buy it. So most power meters, so there are two generations of quasi-intelligent solid-state power meters. The original was called AMR, automated meter reading, and the idea was we do this cool measurement thing, and then we just kind of broadcast out usage to anybody and their brother using a protocol that's pretty well known. And people would drive, like employees would drive by the meters and capture on a device, this meter has this much usage, blah, blah, blah. So in other words, the people who had the boring job of going around and looking at everybody's meter now have the even boringer job of driving down the road. Second generation of intelligent meter came as what we call advanced meter infrastructure, metering infrastructure, AMI. AMI came with basically your iPhone plugged into your power meter. Oh, great, here's the best part. With a disconnect switch. What's a remote disconnect switch? Somebody asked me. A remote disconnect switch is the thing that could definitely change the face of the Western world in the advanced metering infrastructure. But for the short Cliff Notes version, wait, that was the Cliff Notes version. The more broad spectrum version is that the remote disconnect switch allows a utility to send a signal to your meter and shut off power to your house. I mean, the meter still keeps getting its juice. It doesn't care. It's just running along. Most meters who do AMI run on their own proprietary NAN protocol, Neighborhood Area Network Protocol. If you want to think about it in terms you're very well aware of, it'd be like Wi-Fi, only their own version of it. There's another side of the wireless for a lot of power meters. It's called the HAN, or the Home Area Network, that's out of scope for this right now. A lot of that runs Zigbee, if you've heard of it. And there's some other proprietary stuff there. But right now, the focus was on the NAN. Why? Because if, as a security researcher, I am able to plug in something, start up some program, and discover all the meters in the mesh around me, Oh, and maybe ping them. I can now have I can now have a platform from which to test security. Now, this was not intended to drive down the road and be power begone, you know. And if you use it, don't tell anybody that it was my tool, okay? Right. The radio, as I said before, the same radio is used in most power meters. And so it just seemed like an awesome conclusion that if I use an IME dongle, or an IME, which was my original goal, to go hack meters, wow, how cool would that be? In the process, I got to know the USB side, and I just fell in love, and RFcat was born. Wow. We in the security field have become possibly used to vendors understanding that we are a pain in their butts and we're not going away, and that it is for their own good that they need to listen, right? Power industry is not quite there yet. They're about a decade behind, and yeah. So AMI, actually, the AMI people, they kind of get it. They get the idea that we're screwed if we don't listen. Let's do this right. Some of them. I wish I could name a certain vendor, but they've asked me for anonymity. But they have been very good about working with me and with others to find out how their baby's ugly so they can fix it. Some of you in the industry, you know exactly who that is. Others, however, are not. In fact, earlier this year at ShmooCon, a talk was pulled and a tool held back from release based on false fear. And a stupid vendor who will not be named at this point in time. Kevin will name them. This is the segue in the talk. Wow, you got to be careful. You got to be careful. And then there's the people who think that that the RF transmissions are going to cause you more cancer. Hello? There's a phone around here somewhere. That's a little more concerning to me. However, ignorance, when did it become a point of view? I have no idea. But it still works in the smart grid industry. Let me disclaimer that. There are some very intelligent people who understand what's going on, and they're trying to fix it. So power meters are not so easy as a insulin pump. The protocol uses a little hook of the FCC rules saying that they can use a heck of a lot more power to transmit long distances as long as they spread it out over 50 channels. So this introduces something called frequency hopping spread spectrum, and this is the thing the vendor at first thought was so great. Turns out it's a little pain in the butt. RFcat has firmware, has some rudimentary vanilla code to do frequency hopping. You need to give it a set of channels and how far apart they are and how fast they hop. And then you need to write a synchronization method, a discovery method anyway. This, hopefully, for those of you who are going to attack power meters legitimately and not in a way that causes me to lose power, this will get you close enough that hopefully in your paid engagements, you can write your own little widget that says, oh, owned you. Almost done. Come on. This is a gratuitous picture of my Celea Logic Analyzer output. It's beautiful. Runs on Linux very well, which is something because some of the other software really sucksores. Took the dump from the Celea Logic Analyzer between a particular meter main board and the communications chip, and was able to turn that into commands to the radio. Some of it is kind of whitened out for your benefit. Turned on Discover mode, and I knew what these puppies were supposed to look like. This was the 15 potential sync words, so I turned on Discover mode with a list in mind, and I got nothing. And after banging my head truly 5 months, it hit me. It's bit inverted. So every 1 is 0, every 0 is 1. Holy shit. What? Who did that? Why? Add to that the complications of the radio that works at 900 megahertz and bounces between 902 to 928. Was set to 400 megahertz and it never hopped, ever. What? After further analysis, it turns out the radio is heterodyning. You guys familiar with heterodyning? You've got a super het radio in your car, I almost guarantee it. The idea is you take radio signal and you use a mixer to turn it into an intermediate frequency where the components needed to analyze and generate signal very accurately are way cheap. So generating signal at 900 megahertz costs a lot of money to do it well, but at the 52 kilohertz or whatever the intermediate frequency is, you can spin signal on there, heterodyne it up to whatever you need, and it's easily calibratable and cheap. So these guys were taking not only a radio that's doing heterodyning in itself, but then mixing it with a 1.3 gigahertz signal generator, configurable, and they were doing the hopping on the signal generator. Same SPI bus. Yes, I know they're going to kick me off. You may have to carry me out of here. I'm almost done. But I think that in the mix, that's where they threw the bit shifting, and we ended up with a win. If you're interested in doing this work, contact me. I've got my email address on the slides. I know some people who do this professionally. If you're interested in helping out, here are some patents that detail in full detail how the Mac and Phi works on some meter vendors, one in particular. So Marconi is giving a demonstration much like this to very smart people, actually physicists and engineers. And he's on a mountaintop with a big transmitter, and his assistant is in the room, and he's about 5 minutes out from doing a demonstration of this private channelization coolness when some noise is jabbering from the device. So who knows Morse code? So this guy hears the device and starts taking note, figures out that it is Morse code, and somebody is mocking Marconi mercilessly about his virtual private radio. Furious. I mean, the thing was done. People were leaving. It was awful. Furious, they took on the guy in the newspaper. Guy came forward. Neville Mascaline was a circus dude. His family owned a circus. He was a third-generation circus guy. He knew about radio. Why? Because it worked in the circus. You want to read somebody's mind? You have somebody in the crowd feeding you information, right? He had blasted down signal, taken over the device, made a fool out of everybody. Marconi, you saw what he said earlier. I refuse to demonstrate to anyone who casts doubt upon the system. What? His other guy, oh my gosh, his assistant berated him, shredded him, called him a fake scientist and an awful person. And Neville Mascaline's response? Abuse is no argument. In conclusion, I think RFCat rocksters. You can think whatever you want. It's a foundation that hopefully will let you achieve your research goals. Be responsible. Keep vendors on task, but please don't take out my power. Don't kill my friends. Enough said. One last gratuitous slide for my email address if you want to email me. Got references at the end of the slide deck and my greets. Thank you very much, guys. Appreciate it.